Welcome back. This is the second last day of lecture material. This is Physics 360, Week 13, Day 2, scheduled for release on April 17th. And today we're going to be discussing Poisson's equation and solving partial differential equations by means of Laplace transforms. Just a reminder about some outstanding due dates. Due today is the daily homework that was assigned on Tuesday. And Test 3 also opens today. It is due a week from today by 1 p.m. on April 24th. Next week, Tuesday, we have no lecture because Epic Expo was originally planned for that day, but Project Draft 2 is still due next week, Tuesday, even though there will be no lecture posted and no daily homeworks due on that day. Last, we have due on April 24th, the daily homework that's being assigned today that is just one problem, Chapter 13, Section 8, Problem 1. The only other outstanding due date is April 28th, and that is the day that your last periodic homework is due. That's the one about Chapter 13 that I assigned the problems for last time. So with that out of the way, let's get into today's material. So first we're going to start by talking about Poisson's equation. In the entire first part of this section in the textbook shows that Poisson's equation is used for exactly what we claim it was used for at the very beginning of Chapter 13. That U in Poisson's equation represents the potential for a region that contains sources. Maybe that's an electric field in the region, or the electric potential in a region that contains charges, or the gravitational potential in a region that contains mass. But we want to convince ourselves first that Poisson's equation is actually useful for these situations. So very quickly, before we get into that, let's remind ourselves what Poisson's equation looks like. The Laplacian of u equals some function, only in terms of spatial variables, called the source function, where u represents the potential, maybe electric, maybe gravitational, maybe something else, for some region in space which does contain sources of that potential. So let's work through this to convince ourselves that Poisson's equation does in fact cover these situations by considering the gravitational potential. We have the gravitational force field equals negative gm over r squared times the unit vector u, and the gravitational potential is negative gm over r. And let's clarify this by writing that down and drawing a diagram. So down here at the bottom, I have drawn a diagram to show you what these variables mean. We have some point mass, m, that is creating a gravitational field or a gravitational potential at point P. R is the distance between these two locations, and U is a unit vector that points from the mass in question towards the point where we're trying to learn about the gravitational field or the gravitational potential. We're going to start this explanation by claiming that the divergence of F is equal to 0. This is not something I'm going to show right now, but it is your homework problem, and it's a fairly straightforward explanation. I would just recommend using spherical coordinates. So, we also know that any conservative force, or force field F, and its associated potential, V, are always going to be related by the negative gradient. That is, we can write that F equals the negative gradient of V, which allows us to rewrite our divergence of F equals 0 equation, because since F equals negative the gradient of V, we can write this as, pulling the negative out front, the divergence of the gradient of V. And the divergence of the gradient is just the Laplacian. So this becomes the negative Laplacian of V equals 0. So we can say that the Laplacian of V must also equal 0. Or in words, V satisfies Laplace's equation. Now this was just the potential for a single point mass. What if we had multiple point masses? Well, in this case, we could find the total potential at point P by finding the potential at point P from each individual mass and just adding them all up. So mathematically, the overall potential at point PV can be written as the sum over all of the individual point masses of the potential created at point P by that individual mass, which we could also write as negative the sum over all of the masses g m sub I over r sub I, just plugging in the formula for the gravitational potential. And then the force would be related to this in the following way. So the force, the total force field acting at point P, will be the sum of the negative gradients of the potential from each individual mass summed over all of the masses. And if we pull that negative outside and sum over everything, we get, again, that the force is equal to the negative gradient of the potential. So that is still true. So in words, this line is true, still assuming there is no mass at point P, which was one of the key features of Laplace's equation. So as long as we assume that there's no mass at point P, then even if we have many point masses, our V will still satisfy Laplace's equation. The next step as we continue to ramp up the complexity and thus the generality of this statement is, what if we have a continuous mass distribution, not individual point masses, again, with no mass at point P? So what that might look like is something like the diagram I've just drawn. We have an entire volume of mass right here, and that volume we're going to call tau. And we want to know the gravitational potential caused by this entire volume tau at point P. So we can do this by means of integrals. We break up our overall volume into tiny little chunks of mass, each with a mass dm, where dm is going to be equal to rho, the density of this chunk, times the infinitesimal volume in that little square, and then we can add all of these up. But again, there's still no mass at point P, so we should still expect this to satisfy Laplace's equation. Now in this situation, we could write our potential as an integral. And that integral would be negative volume integral over all of tau of g dm over r, where you can replace dm with rho dt, where dt is our standard volume element, dx, dy, dz in Cartesian coordinates. And the contribution from each piece of this mass distribution will satisfy Laplace's equation, so the entire distribution will as well. So what we've done now really doesn't have anything to do with Poisson's equation just yet. We've been considering the gravitational potential at this point P, either from a single mass, from a series of point masses, or from a continuous distribution of mass. And in all of these cases, there is no mass at point P. And in all of these cases, we've shown that our V will satisfy Laplace's equation. So now we want to vary this up a little bit, and we want to construct a situation where we do have mass at point P, and we want to show that instead of satisfying Laplace's equation, this should satisfy Poisson's equation. So we're going to do that in the following way. So we are going to start with some overall mass distribution where the point P is within our mass distribution, But we're going to carve out a hollow sphere of this mass distribution around point P, where the radius of this sphere is A. And let's define some terms here because we're going to have a few different F's and V's floating around in this problem, so I want to get those all written down right now. So F prime and V prime are going to refer to our values for the force field and the potential with the sphere S removed, so with that hollow area in place. Fs and Vs are going to be the values just for the material within the sphere, for just S. And then F and V are going to represent the entire distribution. So this means that if we want the force field at point P for the entire distribution, we can find the force field for the entire area with the sphere S removed, and add to that the force field from just the material making up the sphere. So when we take the gradient of the overall force, something interesting happens. So the gradient of F is going to be equal to the gradient of F prime plus the gradient of Fs. Now we can't just set this equal to 0 anymore because we now have mass at point P. But if we look just at one small piece of this equation, specifically the gradient of F prime, well, if we're just considering F prime, which is again the entirety of the region but with the sphere S removed, well, for that portion of the overall mass, there's no mass at point P. So we know that the divergence of F prime is equal to 0 because this has to satisfy Laplace's equation. So this means that the divergence of F is going to be equal to the divergence of Fs. So if we want to know the divergence of F, we can just try to find the divergence of just the material within that hollow sphere. And we can do this by using the divergence theorem. So we know that the volume integral over the entire sphere S of the divergence of f of s is going to be equal to the surface integral over the surface of the sphere S of fs dot n hat, where n hat will be the outward-facing normal around sphere S. So that would be in this direction here or in this direction here, always pointing radially outward from the surface of the sphere. And what we're going to do here is we're going to let a approach 0. Because if we take the limit of everything as a approaches 0, we get an answer that is equivalent to the potential at point P as though that sphere were never removed to begin with. And as we let a approach 0, the left side of this equation, the volume integral, becomes almost trivial. Because the divergence of Fs might vary at various points throughout the volume of Fs, but if we let that sphere become infinitely small, then the divergence of Fs becomes a constant. So our volume integral will become the divergence of Fs times the volume of that sphere, 4/3 pi a cubed. Now for the other side of this equation. At the surface of the sphere, the force is equal to, at least in magnitude, gm over a squared, where m is the mass inside the sphere. So the mass inside of that sphere will be equal to the volume of the sphere times its density, so that we can say that m is equal to rho times 4/3 pi a cubed. And at the surface of S, the normal vector may point outward, but the gravitational force field is going to be pointing inward. So this means that our dot product will just give us the product of the two values with a negative sign. So now we've evaluated the left-hand side and the right-hand side of this separately, so we can now set them equal to each other. So we have from the left-hand side the divergence of Fs times 4/3 pi a cubed has to be equal to negative 4/3 g pi a rho. And then when we take that integral over the entire surface, we get the surface area of the sphere added or multiplied to this side. So just like we saw above where the divergence of Fs was constant through the entire volume, so the integral can just be rewritten as that divergence times the volume, here we have Fs dot n hat, which is going to be constant over the entire surface of the sphere. So we just have the value of that dot product times the surface area of that sphere. And from this, we can then cancel some things out and obtain the following equation. So the divergence of Fs equals negative 4 pi g rho at point P. And we know from before that the divergence of Fs is equal to the divergence of S from back over here. So we can rewrite all of this in the following way. The divergence of Fs is equal to the divergence of F, which is equal to negative 4 pi g rho. And we also know that the divergence of F is equal to the negative Laplacian of V. So we can now write that the Laplacian of V is equal to 4 pi g times rho. And this is Poisson's equation. This is Poisson's equation where the source density is 4 pi g rho. So this means Laplace's equation, Poisson's equation does represent what it claims to represent. It represents the potential at some point within a mass distribution, so that we can find the potential, the gravitational potential, anywhere in this region, not just outside of this region. So we can now include mass at point P. And if you're worried about the 1 over r in our original equation for the potential, so if you're worried about this r right here, that r becomes 0 at point P. So shouldn't this explode? And I want to convince you at least really quickly that this is not the case, that this does not explode at point P, because d tau, the volume element, will be written in spherical coordinates here. So this integral then becomes, with the appropriate volume element for spherical plugged in, the following. So now we have this extra r squared sine theta term, but the important thing is that we have an r squared in the numerator and an r in the denominator. So there are no problems with r being 0 in this equation. So we have hopefully convinced ourselves that Poisson's equation is valid for the potential in a region containing sources, and that our math is not going to explode because of a divided by 0 when r equals 0. To write things a little more generally in a little less abstract proof form, we can now say that u, which is equal to negative 1 over 4 pi times the volume integral of f times d volume over r, is going to be a solution of Laplacian of u equals f. Or, in more detail here, so u as a function of x, y, and z equals negative 1 over 4 pi times the volume integral of f of x prime, y prime, and z prime over the square root of x minus x prime squared plus y minus y prime squared plus z minus z prime squared, integrated over dx prime, dy prime, and dz prime, is a solution of the Laplacian of u equals our source density f. So I want to clarify the difference between x, y, z and x prime, y prime, and z prime here. X, y, and z specify the location of point P. Basically, at what point do you want to know the gravitational potential or the electric potential? X prime, y prime, and z prime refer to points within our mass distribution. So integrating over dx prime, dy prime, dz prime means we integrate over our entire mass distribution. So one thing to note is that this formula that I've boxed above gives you a potential that is 0 at infinity. Now, for many situations, this could be useful. The standard definition of gravitational potential is such that it's 0 infinitely far from every other object. But for other situations, like with electric potential, we might want u to equal 0 somewhere else. So what do we do in this situation? So to do this, we will find a new function w that satisfies Laplace's equation, not Poisson's equation, and then we will add that to u to get our final answer. And just to verify that the function u plus w does still satisfy Poisson's equation, so if we take the Laplacian of u plus w, then we get the Laplacian of u plus the Laplacian of w. And because w satisfies Laplace's equation, its Laplacian is 0, which just leaves us with the Laplacian of u, which we already knew was equal to f. So now we can say that the Laplacian of our new function u plus w equals f. So this means our new function u plus w still satisfies Poisson's equation. Now, all of this still probably feels pretty abstract, so let's do a specific example. We're going to do the example your book does, which has a grounded sphere of radius r located at the origin, and we're going to put point charge q at a location A on the z-axis, where A is outside the sphere, and we're going to try to find the electric potential everywhere outside the sphere. Now, one thing we should do here is convince ourselves that this really is a situation where we need to use Poisson's equation rather than Laplace's equation. And since we're trying to find v at any point outside the sphere, we need to check whether there are any sources of electric potential outside the sphere, i.e. charges. And point Q is outside the sphere. So we are trying to find the potential in a region that does contain charges, that does contain sources of the potential we're trying to find, so we do need Poisson's equation. And in this situation, Poisson's equation becomes, with Gaussian units, the Laplacian of v equals negative 4 pi rho, where rho is the source density, or the charge density in this case. So we could actually write rho as a delta function. This was actually one of your previous homework problems, something like this. So we have a density. We want to get q, the charge, back out once we integrate over everything. So there's a q out front, and then 3 delta functions specifying the x, y, and z location of this point charge q. So based on what we discovered in our previous example, we know the solution to this equation. So we've simply taken the result from the previous problem, or from the previous slide, and plugged in negative 4 pi rho into our numerator. So this integral is actually very trivial because it contains a delta function. So the only places this integral has any value whatsoever is at x equals 0, y equals 0, and z equals a. So effectively, we're just subbing in 0 for x prime, 0 for y prime, and a for z prime. So we get the following. q over the square root of x squared plus y squared plus quantity z minus a squared. And the problem is that this potential is 0 at infinity, but we have a grounded sphere of radius r, and the electric potential is defined such that any grounded object has a potential of 0. So briefly, I want to rewrite v in spherical coordinates and give it a different name, because this is not going to be our final answer anymore. We are going to call this vq, and in spherical coordinates, that looks like the following. V sub q is equal to q over the square root of r squared minus 2ar cosine theta plus a squared. And what we need to do here is find a solution to Laplace's equation that we can add to VQ so that the sum gives us 0 at little r equals big R, i.e. on the surface of this grounded sphere. And that is what we are going to do next. And our solutions to Laplace's equation in spherical coordinates are something we found before. For the r part, we have either r to the L or r to the negative L minus 1. Then we have the associated Legendre functions of cosine of theta. Then we have cosine of m phi or sine of m phi. And we can apply some boundary conditions here. We want to know the potential everywhere outside the sphere, which means our solutions must be finite at r equals infinity. So we have to discard our r to the L solution. We also know that our charge distribution is symmetric with respect to phi. So we need a solution that is also symmetric with respect to phi. So like we have before, we're going to use cosine of m phi with m equals 0 so that cosine of m phi equals 1. So we're now ready to write down the form of our final solution, even if we don't know all of the details yet. Our overall solution will be VQ, the original solution to Poisson's equation, plus this solution to Laplace's equation, which can be written as the sum over L of the coefficient C sub L times r to the negative L minus 1 times the Legendre polynomial of cosine of theta. Recall that when m equals 0, the associated Legendre functions just become Legendre polynomials, but we still need the potential to be 0 at the surface. So let's try to make this happen. So we need our v evaluated at r equals big R, which equals q over the square root of big R squared minus 2a big R cosine theta plus a squared, plus the sum over L of C sub L big R to the negative L minus 1 times the Legendre polynomial of cosine of theta. And it's going to be helpful here if we can expand this first term right here in a Legendre series. So as a linear combination of Legendre polynomials so that we can add these two terms together more easily. It turns out that this process is fairly straightforward because our VQ is very similar to the generating function for Legendre polynomials. So if you want more details here, you can see equations 5.12 and 5.17 from chapter 12. So this VQ term becomes Q times the sum over L of big R to the L times the Legendre polynomial of cosine theta divided by A to the L plus 1. So now we can just say that for any given term of L, everything has to sum to 0. So we can write that as follows. And I've canceled out the Legendre polynomials with respect to cosine theta because those appeared in both terms. So if this that I've just written as yellow is true, then that means we know that our potential, the total potential, will be 0 at the surface of the sphere. So from this, we can then solve for CL as the following quantity. So we get CL equals negative Q times R to the 2L plus 1 power over A to the L plus 1 power. So before I write this down, I want to make myself a little more space here, and I wish I had written a little more small at the very beginning of this process, but I'm just going to clear some of the beginning space that we worked with. So now that we know our values for C sub L, we can come back to our original final answer for V and start to plug in our values for C sub L. So we have our original function VQ in spherical coordinates minus Q times the sum over L of big R to the 2L plus 1 times little r to the negative L minus 1 times the Legendre polynomial of cosine theta divided by A to the L plus 1. So what we are going to do now is we are going to actually sum this series. Now this summation that I just did is not trivial, and if you're interested, it's problem 2 from this section of the textbook. I'd be happy to send you the solutions for it if you'd like. But even though we've reached our final answer here, I want to draw your attention to something that you might not notice that actually relates to something you may have learned in another class. Specifically, this second term here, the solution to Laplace's equation that we added to our original solution so that the potential could be 0 at the surface of the sphere. This term, the one I've underlined in green, is the same as the potential for a specific point charge at a specific location. So if instead of everything else we did, we just took a single point charge with a charge of negative RQ over A, and we placed it at the location 0, 0, R squared over A, we would get the exact same potential at all points outside of the sphere. And because of this fact, this method of solution is known as the method of images, which can be a very helpful way for simplifying complicated problems involving grounding in electrostatics. We could have also solved this same problem by using Green's functions instead. So to solve, the Laplacian of u equals some function that depends on position, being our source density. We first solve the Laplacian of our Green's function equals a delta function centered on the point r prime, which is x prime, y prime, z prime. So then the Green function here is the potential due to a point source. Then, once we know our Green function, then we can solve for u in the following way. So we know u could be solved by the volume integral over the volume tau prime of the Green's function times our source density as a function of r prime. But we also know from our previous work that we can write the solution to u another way. So by comparing these, we can find our Green function, which is equal to negative 1 over 4 pi times the magnitude of r minus r prime. But we still have the same issue we did before, because we have two different equations, this equation here for our green function and this equation up here that is related to what we've done on the previous slides. And both of these functions are 0 at infinity, so we again need to add an offset. But this time we're going to add an offset to our green function. So we are going to write our new greens function in the following way. We're going to take our original green function and we're going to add to it a function capital F of r and r prime, where this new function f must satisfy Laplace's equation. Then, once we have our new green function, we plug in to the following integral to get our final answer to this entire problem. So this is the same as the usual solution to a Green's function problem. Now, I don't have time to do the entirety of this example here, and this lecture is already going to be a little long and involved, but as it relates to the example we were doing, we would get the following green function for our solution. There, our Green's function is equal to negative 1 over 4 pi times the magnitude of r minus r prime plus the extra term big R over r prime all over 4 pi times the magnitude of r, little r, minus big R squared r prime over r prime squared. The last thing we're going to talk about fairly briefly is Laplace transform solutions to partial differential equations. We solve things using Laplace transforms for very simple ordinary differential equations, but we can actually apply this to partial differential equations as well. And I want to explore the problem of the semi-infinite bar that extends from x equals 0 to x equals infinity with insulated sides that is held at 0, and then at time t equals 0, the end at x equals 0 is now held at 100 degrees. So this is going to be a heat flow equation problem because, well, it's not steady state temperature because the temperature will be changing over time. So we need our differential equation, our u, what we're solving, will satisfy the differential equation. The partial of u with respect to x, double partial, equals 1 over alpha squared times the partial derivative of u with respect to t. So instead of assuming a separable solution here, we are going to define a function. The Laplace transform of little u is going to be equal to big U. So this is our standard definition of a Laplace transform. So in other words, we could say that the Laplace transform of little u equals big U. So this means the Laplace transform of the partial of u with respect to t is going to be equal to p times big U minus the value of u at t equals 0. And the temperature in the entire bar is 0 at t equals 0, so this just becomes p times big U. Then we also need to take the Laplace transform of the double partial derivative of u with respect to x. And, well, the Laplace transform has to do with t's and p's. So this partial derivative with respect to x is really kind of like a constant, and we can pull it out front. So this becomes the double partial derivative with respect to x of the Laplace transform of little u, or the double partial derivative with respect to x of big U. So our original differential equation then becomes the double partial derivative of big U with respect to x equals 1 over alpha squared times p times big U. And if we think of p as a constant, this is basically just an ordinary differential equation. And the solutions of this ordinary differential equation are big U is either e to the square root of p over alpha times x, or e to the negative square root of p over alpha times x. Now we need to apply our boundary conditions. But when we apply our boundary conditions, we're applying them to big U, not little u. So we are going to need to Laplace transform our boundary conditions. So the boundary condition that little u equals 100 at x equals 0 will become big U equals the Laplace transform of 100, which is equal to 100 over p at x equals 0. And the Laplace transform, or rather our boundary condition that u equals 0 at x equals infinity, will have to become big U equals the Laplace transform of 0, which is just 0, at x equals infinity. Well, if our function big U has to go to 0 at x equals infinity, that means we can discard our positive power solution. So we can now write our solution U, big U, as the following: 100 over p times e to the negative root p over alpha times x. And then we just Laplace transform this back. And we will be using the rule L22 from your table here to find that little u is going to be equal to 100 times the quantity 1 minus the error function of x over 2 alpha root t. So you can look up more about the error function if you want, but this pink equation would be our final answer to this question. The error function is basically the integral of a normal distribution. Now there is more stuff in this section of the textbook that we're not going to cover. It's all about integral transform solutions to partial differential equations, and we just did the Laplace transform. There are also Fourier transform solutions to partial differential equations that we simply don't have time to get to today. So that's everything we're going to get to today. Thank you for watching and putting up with me through a long lecture. Things will not be quite so mathematically overwhelming for our final lecture next week, Friday. But either way, thank you for watching and have a good day.